Hey everyone, in this video we'll be continuing on with the SageMaker Inference and Hosting series, and we'll specifically follow up with LLM hosting in specific and revisit a construct that I talked about in the multi-model hosting options video, and I'll link that down below. What we'll specifically explore is a new inference feature known as inference components, and this is a way that we can efficiently host LLMs on a singular endpoint from both a performance and cost angle. And what we'll do is we'll talk about why exactly we can't use multi-model endpoints and why that's not an optimal hosting option here. I know we got hands-on with that before when we deployed those hundreds of scikit-learn models, and we'll speak as to exactly why we need inference components and what are the different use cases you can apply them in. And we'll also talk about what is new about this feature. What exactly are we adding on to in terms of the already existing kind of SageMaker inference constructs. And we'll also kind of, at a high-level overview, how you can enable per inference component or model scaling. What's the difference between that and endpoint scaling, managed scaling, different kinds of concepts that we'll talk of. And just to clarify all these so you can see them all working too, we'll have a hands-on notebook where we deploy both a Quen and OpenLlama model using inference components on a singular endpoint. So that's kind of what we could look at as a high-level outline for what we'll be working with today. And without further ado, let's hop right into the whiteboard as always. And before we get to SageMaker, what I did want to talk about is maybe use cases, right, where you might need multiple LLMs or things that I've seen at least in the field for when this happens. So use cases for LLMs or multiple of them in a single use case, right, that you might want to think of is maybe you have a Q&A chatbot, and then with that Q&A chatbot, you might have a audio-based large language model. So that's obviously a different modality. Maybe you have an audio-based large language model that's doing transcription, butchering spelling as usual, and then real-time, like maybe sentiment analysis or things of that sort. Just different kinds of things like that. And then maybe you might have another LLM that also does summarization. So of all the different texts that you're working with, or all the different, depending on the entire conversation that's happening, maybe you want a summarization and then with the key points kind of generated. Different LLMs can be good for different tasks. So it's very, very common to have multiple LLMs. Or maybe you just have a list of different kind of generative AI hosting use cases, and you have multiple different LLMs achieving different things, right? So there's a lot of use cases where really in a production setting, and it's maybe not just one LLM where everything's centered around. You might also have, as we discussed right now, multiple LLMs or maybe even other GPU-based models. And a common use case for this is RAG, right? In RAG, you have an LLM and an embeddings model. And you might have multiple embeddings models depending on if you're working with different kind of modalities or different kind of use cases there. So there's many different use cases where you have GPU-based models that you might want to host on the same endpoint. And traditionally, right, we talked about multi-model endpoints, which we got hands-on with, and we showcased how you can host multiple scikit-learn models on CPU-based instances. Now, there's also GPU support within MME, but the problem is, at the moment of this video, at least within MME, there's only support for machines that are single GPU based instances essentially. And this leads to challenges then, right? Because with single GPU instances, we can't really shard a model. And as we saw in our LMI hosting video, most of these LLMs, you need to be able to have multiple different GPUs for which you can partition this model across for efficient inference and performance there. So multi-model endpoints, it's a little difficult. And like we said also, there's some limitations or some constructs that you have to abide by. And it's completely okay if your use case is suited for those, but you only have a single container. So if you have different serving stacks, for example, for like your embeddings model and your LLM model, you can't bring that because there's a single container that is persistent across the entire endpoint, and all models there must utilize that container. And there's no per model scaling. So let's say that you know your Q&A LLM needs to scale up individually and free up more resources for that behind the endpoint. You cannot enable that within multi-model endpoints. Let me say it's not supported. Right here, sorry. Make that a little clearer, not supported right there. And we can see that there, right? And this is essential, like we said, with LLMs, right? Because if you especially know which model might be receiving a majority of the traffic, you can kind of scale each component or each model by itself. Whereas with an MME, all the resources are shared by all models. So whatever compute you have behind from a memory and kind of course perspective or worker's perspective in terms of the number of CPU cores you have behind. All these resources are shared by the multi-model endpoint. Once again, these are not problems. It just depends on your use case. Now with inference components, right? What's been introduced before I even go to that diagram there, with inference components, we inherit a SageMaker model object. And the SageMaker model object, if we remember right, this points towards the model data and container. So this is all the exact same. But what's been added with inference components is a few features. So what's new? Let's maybe make this a section right here, is you can specify your hardware resource requirements, and we'll show all this in the code too, in terms of how it maps. And for this, right, you can say, for example, reserve 4 GPUs, and then maybe X amount of memory, and X amount of CPU cores, whatever it is, right? Whatever you're working with there. And then another thing that you can specify is something known as copy count. And when I was referring to per component or per model scaling, this is what I mean. So every copy of the inference component retains essentially the hardware resource requirements that you've specified. And you can scale on a per component basis with this new metric essentially. So if you know, for example, when we were auto scaling before, right, at the endpoint level itself, we were saying if you're hitting 10 invocations per instance, then scale out. In this case, we'll say if you're hitting 10 invocations per copy, then increase the copy count, and each copy will retain the amount of hardware that you've specified or allocated per. So let's say that your copy count scales from 1 to 2. That's 8 GPUs then reserved for that component or model. And what you want to ensure then, right, is at the endpoint level itself, this is another what's new, I guess, here, is there's managed auto scaling. So what you could set is a min-max, and we'll look at this a little deeper here, and it might be a little confusing at first. You can set a minimum and maximum instance count. Let's say we have a GPU instance that has 8 GPUs behind it, right? So let's say our GPU instance has 8 GPUs. And then with these 8 GPUs, let's say we have 2 different models, Llama and maybe Falcon. I might just be making up the numbers here in terms of requirements. And each one needs 4 GPUs per copy. And you enable scaling for each of these to scale up to 3 copies each. 3 copies each means 3 copies each at full scale out means there's 12 GPUs, 12 GPUs at full-fledged scale out potentially if both thresholds are hit at the same time for auto scaling being triggered. That means, right, we need to set a max value for our managed auto scaling that can add up to the maximum of our components. So for 24 GPUs, right, we're probably going to need at full out max scaling 3 GPU instances, each with 8 GPUs. And what will happen is SageMaker will first scale out the endpoint level resources to that amount, and it will scale up each component as well to reserve the amount of kind of GPUs you specified in terms of the per copy limit. So for example, if Llama just scales to 3 and Falcon just scales to 1, then you have 16 GPUs that are reserved behind the available 24 GPUs right there. I don't know if I butchered the math, but essentially the idea is you can set up managed auto scaling. Don't really worry about setting any metrics or anything there. Just that will scale out depending on your per component scaling. The only thing you need to ensure is that at full scale out for each component, you've allocated enough on your max instance count to match the hardware resource requirements there. So you have to do a little quick math there just to understand it. And we'll showcase how you can enable managed auto scaling as well. But that at a high level is what's new in terms of the inference component itself. Now for the construct in terms of how we'll define it, very, very similar to our original flow. If you remember, we had SageMaker model, we had our SageMaker endpoint configuration, and our SageMaker endpoint. What we're going to do now is actually a little different. We're going to flip things. We're going to first create that endpoint configuration where we specify the hardware and any variants. And in this case, we actually also add managed auto scaling at the endpoint level once again, right? We enable that, and then we create a SageMaker endpoint just like we would, but we actually can't invoke this yet because there's no components behind it, there's no model data or anything, right? So what we then do is we create a SageMaker model object And like I said, this might seem a little counterintuitive for what we've learned so far. The SageMaker IC object inherits that model object. So here we specify the model data and container like we always would. And what the IC does is it absorbs that model and it adds those hardware resource requirements and that copy count, and then you can create these. And this, just like the endpoint, will take a few minutes to create because we're provisioning the resources underneath the hood depending on what you've specified for the hardware resource requirements. And you're enabling that copy count. And once you've created this, just like an MME or any other endpoint, you can do invoke EP, but there's a new target IC header. So you can specify, oh, I want to invoke llama here, or I want to invoke Quen, whatever I'm working with, right? So just like MME where you specify the target model, you're going to specify the component name. So all the same kind of tools or theoretical concepts, you can just think of this as us adding kind of that hardware resource requirements on top of it, enabling per model scaling. And that's very, very useful in the LLM world, especially, right? Because if you know you need a certain amount of hardware behind a certain endpoint, or sorry, a certain LLM to serve it, then you can reserve that and you can scale it as appropriate and as necessary. So with that being said, let me get out of the slides and the whiteboard here, and let's hop into our usual familiar console that we've been working with in this series. I'm in the SageMaker AI console. I have a notebook instance created. I also have a studio domain created at the moment, and I'll explain why in a second, but I would create this domain here because at the moment, at least, of this video, there's no UI where you can see the inference component itself, but it's available within Studio, and we'll explore that once we've created the components. But for development itself, right, just I'm in the classic notebook instance that I'm working in, and this will all be that same GitHub repo that we've always worked with. So if I come here into my notebook that I've pre-created this stuff. This might take a little longer to run. Like I said, there's time to create the endpoint and inference components at this point of time. Here we see that same structure that we just kind of drew out, the endpoint config, the endpoint, inference component, and then invoking that SageMaker endpoint, right? All those same constructs, just this new feature here introduced where this inference component inherits from that model. Our tools of use are going to be the same. The higher level SageMaker Python SDK for any utilities, Boto 3, which is the lower level AWS Python SDK. I set up my clients, one to create these constructs, one to invoke the usual stuff. And like I said, here we're first going to create the endpoint configuration object. The flow is a little different from the traditional SageMaker endpoint. And in this case, we use an 8 GPU machine. You might need to submit a limit increase request for 2 of these. I did that in the service quotas essentially, and you should get that approved before you can run this notebook. But here I create my endpoint configuration. If you notice here, I define a few things. I say my initial instance count is 1, my max instance count is 2. So this will be the managed auto scaling that I'm going to enable. And you can see in this create endpoint config, there's a new key here in production variant saying manage instance scaling is enabled. And at max, I know that I'll have 2 instances or 16 GPUs that I can work with essentially, right? So this is the max instance count that I've enabled. And if we remember in the LMI container video we were talking about, I'm also going to enable LOR routing strategy, which basically serves traffic to the instance that's most fit or able to receive those requests at the moment. So I enable that. I set a few other parameters in terms of container health check timeout so that doesn't time out while pulling down these model artifacts. But the main thing here is we're enabling managed instance scaling at the endpoint level. And we won't apply auto scaling on a per component basis in this video. We will do that in the follow-up. But the idea here is we no longer have to take care of it at the endpoint level itself. I've created this. I can see my min and max instance count. I create my endpoint. This takes a few minutes to create. But like I said, this endpoint's useless at the moment because there's nothing to invoke behind it. And now we can get to the real magic in terms of hosting multiple LLMs, right? So our inference component, like I said, we inherit from that SageMaker model object, which points towards the model data and container that you're working with. So for our first inference component, we'll take OpenLlama, just like we did in the LMI hosting video, and use the LMI container to deploy this OpenLlama model. And if you want to kind of follow up, just check out the previous video in the channel for it. And this is essentially where we showcase or get a little deeper into what the LMI container is. But here I set up my OpenLlama environment. This model requires 4 GPUs, and I set up the container here in terms of working with it, and I create that model object right there for what I'm going to be using. I essentially then have a new API call after I've created that model object, and that's the create inference component API call. And if you see, for this create inference component API call, I'm going to pass in the endpoint. So I'm going to say whatever resources are behind this endpoint, this is where my component is going to be borrowing from. And within that, I specify a few things. I specify the model object, which is pointing towards my container and my model data and my different serving environment variable files. But the new feature here is these two kind of keys. So in the specification, there's the compute resource requirements that I'm working with. And within that, I enable the number of GPU devices, or this can also be neuron chips, neuron cores, depending on if you're using Inference there. But this number of accelerator devices required is 4 GPUs. So I'm saying for this component, for every copy, ensure that there's 4 GPUs reserved for this component. And then I set some CPU and memory kind of numbers here as well. And you can see here for the runtime config, I have a copy count. I'm just going to start with 1 in this use case because it's a bit of a demo, but this copy count, right? Each copy reserves those 4 GPUs right there, essentially. And if I enable auto scaling, which we'll explore in future videos, it will be this copy count that gets scaled up. And with each copy, this same compute is going to be reserved. So that's what's crucial. You do that math in terms of the managed instance scaling. Because let's say you scale up to 10 copies, but then you don't have enough instances behind it itself for the managed auto scaling to kick into place, you're going to run into errors there. So not much else here. Just think of it as the hardware requirements and the copy count is what we're going to be adjusting and tuning here. And that's essentially what's built. And then next, like I said, this will take some time because the hardware that you're allocating is going to be reserved behind it. And then we create this inference component. Very similarly, we'll use Qwen, just a variant of the Qwen model family. I think it's 7B instructor here. And for this, we'll use the text generation inference container from Hugging Face, which is pretty tightly coupled, so it's easy to deploy for sample purposes like this. It's just another serving stack. We can explore that further in the future, but it's built by Hugging Face there. But essentially what we do is we retrieve the container image for TGI. We take the environment and create the model object for that Qwen-based model. So I'm going to point towards that Hugging Face model ID. I'm going to take my TGI image, just a different serving stack. So this really showcases, though, what I want you to take away is you can use different containers and different serving stacks. With an MME, remember you're constrained to a single container in terms of what you're using. And this is especially useful. I've seen at least when you have an embeddings model, which you might be serving with maybe like Trine Inference server or Torch serve, and then you might have your LLM on a completely different serving stack. So you have the freedom to bring multiple different containers here. I then create that model object pointing towards the container and the specification here with the model data for Hugging Face. I then create an inference component, and here in this case, Qwen only needs 1 GPU, and I specify that, and I specify the copy count to 1. This is not the most efficient because we're probably just using 5 out of 8 GPUs that are available on the machine, but once again, this is for demo purpose. You can think of maybe you can onboard even 2 more models here, maybe an embeddings model that might require a GPU. So it's up to you to kind of do the math out, see what's the best instance type behind the endpoint in terms of what each of your models or components need. So this is definitely not optimal, just this is the sake of demo here. But I enable those same parameters there, just 1 GPU needed for Qwen. I see that's been created, and then I can run sample inference, right? So I'm going to do that same invoke endpoint call, which has been kind of her best friend through this series. And the new header here is we have a inference component name. Just like an MME, there's a target name. I'm going to first specify the OpenLlama inference component name for which I created. So if we go back up here, we'll see that there should be a OLlama IC name, which is pointing towards that OpenLlama model. I can invoke it, get an output. Similarly with Qwen right here, I'm going to specify the Qwen IC name that we created, invoke it, and then I should get an output shortly in terms of it. So very, very similar in terms of the constructs, just introducing one new feature there, and we'll see the output neatly pasted there. And the last thing I want to talk about, right, is where you can visualize or start trying to debug all of this. If you go to Studio, like I said, at the moment, there's no UI for inference components here. But if you go to Studio and you go to your domain once it's been created, and you go down to deployments and click endpoints, you'll see this ICEP endpoint that I've created. And then you can see these 2 different components or models that have been created, the hardware that you reserved for both of them. And for any logs on each one, container logs, you can click view logs, and you'll see the specific container logs for each component that you're working with, because these are different serving stacks that we might be using here, right? So you'll see the logs here for Qwen, I believe, or was this OpenLlama that I clicked on? Yeah, OpenLlama right there. But yeah, in terms of any kind of debugging, it's very, very useful to hop in here and go to the CloudWatch logs there. And then finally, please make sure to clean this up. We're not going to be deleting just the endpoint. You also need to kill those components beforehand because they're holding a certain amount of the hardware behind the endpoint itself. So we run through that end to end. We clean up our resources. Definitely make sure you do here. G548 Excel can get a little hefty cost-wise there. So yeah, I think that was mainly it from this video. I wanted you to understand how you can deploy multiple LLMs in a efficient manner from a cost and kind of performance perspective on SageMaker itself. And what we'll do in coming videos is we'll maybe explore how we can scale up each of these components. So if you know a certain model is going to be receiving a lot of traffic, how can I apply auto scaling to the inference component itself too? And we'll really see the full power of the feature there. But thank you as always for watching. And if you have any questions or any doubts, please feel free to leave them down below in the comments or reach out to me on LinkedIn. If you enjoyed this video, feel free to leave a like and subscribe as well. Thank you, and I will be back very, very shortly.